Thank you, Liberato. My talk somehow reconnects to the first one from Liberato in one way, and concerns how to consider deterioration effects in assessing the potential retrofit of existing reinforced concrete structures. I'm not talking about material, but uh, how to evaluate the durability of structures, and so whether it is worth repairing or renovating or demolishing. We know that if you look at the Italian building heritage, about over 60% of the reinforced concrete buildings were built before the 80s. They are obsolete and engine efficient, and they're usually vulnerable to seismic hazard because they were not designed considering earthquake, whereas Italy is totally earthquake prone. And we also know that the environmental impact of the building sector is extremely high, as it's responsible for 50% of raw material consumption, approximately 35% of waste production, 38% of green gas emission, and 35% of energy consumption. So under this respect, the question arises, demolition, reconstruction, or renovation? If we look at demolition reconstruction, there is a huge problem of waste production and disposal, even invasive and impacting operation, large production of raw materials, relocation of inhabitants, the last point being the main issue. If a building is not empty, it's pretty hard to relocate everybody. The other option is renovation through innovative sustainable solutions. And the idea is to apply a life cycle thinking approach, which entails several steps. For instance, the idea is to use sustainable materials, to consider repairability of the solution, demountability, and deconstruction and end of life, and also updating, upgrading of the building during the life once new technologies come available. Well, we applied these principles to several projects. This is, for instance, a DESA project, and we tackle approaches where we used steel exoskeleton, wood exoskeletons, but also concrete shear walls on the outside, and generally thinking of working from the outside of the buildings without relocating anybody. And we have also done several applications in rear buildings. So there is a future there. However, the problem is quite serious if you look at the deterioration state of the buildings. We have to devise some tools to decide whether it's worth repairing or the building needs to be demolished. And well, the question is like the rotten apple. The apple looks perfect, but in fact it's rotten inside. And what we found is that assessing the state of deterioration of concrete structures, particularly concerning corrosion, is not as easy as it is said. And the main reason is that it involves different type of expertise, and experts that not always talk to each other, not always used to talk to each other. Very often the structural engineer is the one who tackles the building, and most of the time he's not aware about the consequences of corrosion. So we tried to devise a tool, a protocol, which would allow the practitioner engineer to tackle correctly the deterioration evaluation of a building. And so we went through defining, so a first step, a building inspection. Through the building inspection, we gave criteria and guidelines to define a scenario. So let's say a corrosion risk scenario that depends on the environment, on the condition of concrete and so on. And eventually this allows to define, as we'll see, material models let's say, equivalent damage parameters to be used in structural analysis. So we devised 4 types of scenarios, and for each scenario, depending on whether there is no carbonation or chloride-induced corrosion, or there is corrosion only, carbonation only, or carbonation plus chloride ion attack, so presence of chloride ions, or eventually corrosion due to chlorides. So depending on the scenario, through non-destructive test and on-site test, fairly simple test, we end up trying to define risk classes. So we provide a logical path that the practitioner can use. And so this would eventually allow to define simplified engineering design parameters that can be used by the practitioner to assess the residual life of the structure. I'll go through the slides that tend to show how the practitioner should work and try to define the type of risk scenario by looking at the damage type which might be observed and through some simple on-site test. And this is the complete protocol, which has been baptized DEMSA protocol and is available in the literature. But the final goal is this. So the final goal is to put practitioner engineers through proper equivalent design parameters in the position of assessing the residual life. So if A is, for instance, the time of analysis of the structure, and he is able to define the residual life, and this is the design limit condition, he might decide to intervene at A, for instance, with a repair, just trying to freeze the condition without any real improvement, or he could wait up to B, a given time, and intervene to bring back the structure to its original state and therefore relaunching the residual life, or even to enhance the initial behavior of the structure and to relaunch even further. Of course, this is a twofold tools, because sometimes these tools indicates that the only really sustainable solution is reconstructing. Nowadays, it's very difficult to give objective tools that might be used to decide whether a building is worth a renovation process or reconstruction is the only solution. And this is the whole idea of the protocol. The ongoing research in our research group goes trying to recognize corrosion patterns in existing structures, define simplified corrosion patterns which can help the professional engineer to define the risk scenarios I previously mentioned. And now we are starting to work, we started on buildings, now we're starting to work also on bridges, because of course on bridges the issue of corrosion is well known due to the use of de-icing and other issues. So the problem is this kind of research requires a lot of cooperation, cannot be carried out by structural engineers alone, doesn't make sense, cannot be carried out by corrosion experts alone, because the impact on the structure eventually requires the structural engineer. And testing engineers, we need to define simplified tests to define chloride content. There are tests already based on the analysis of powders and so on, but there is much more to be done, and I think this is a way in which it's worth investing. Thank you.